Hey folks, how y'all doing? We are starting section 4.3 today, which is on similarity. This is a short section, but it is a um, concept that I found difficult when I've took linear algebra, so I hope you will not find it as difficult. So let's go ahead and get started. I want to start by reviewing something from chapter 3 um, that allowed us to work with these alternate coordinates. So we have a basis here. Um, this is not the standard basis, but this is still a basis because in the echelon form, we have a pivot position in every row and every column. And we want to convert this basis to standard coordinates. Um, so what this says is that this is 3 units and -2 units, but not in the standard x and y directions, but in the b directions. And so that's saying that we take 3 units of 1, 1 and -2 units of -1, 1 and combine those together, and we get 3 plus 2 is 5, and 3 minus 2 is 1. But this here is exactly the same as multiplying by the matrix 1, -1, 1, 1. That is, if we take these two vectors, form a matrix out of them, multiply it by 3, -2, that's just saying assign the weight 3 to the first column and assign the weight to -2 to the second column, and that's exactly what this is. And so what we could think about this is that the going from the alternate coordinates to the standard coordinates is to multiply by whatever this matrix is, and right now I'm going to call this P. There's a reason why I'm going to call it P, but for right now we're just calling it P. And that matrix just contains the two vectors in P and B combined together into a single matrix. So if we want to convert this vector into B coordinates, now this is the standard vector. We can't do this by multiplying by P. One way we can solve this is to solve to find out how many copies of the B coordinates are needed to make 1, 5. In other words, how many copies of 1, 1 and how many copies of -1, 1 does it take to make the vector -1, 5. And we can row reduce this system, but there's an alternate way of solving this system. This is the system p times x is equal to -1, 5. And that means that x is equal to p inverse times -1, 5. And so if we took the inverse of this matrix, so let's talk about how to do that again. The way that we find the inverse is we take 1 over the determinant of the matrix. So the determinant is 1 minus -1, which is 2. Then we switch the entries along the main diagonal. Well, since they're the same, that doesn't change anything. And then we change the sign of the entries along the other diagonal. And so we get a matrix with a lot of 1/2s in it, but that's okay. positive 1/2, positive 1/2, negative 1/2, and positive 1/2. If we multiply that times negative 1/5, that's the same as saying negative 1 times the first column plus 5 times the second column. And so we get negative 1/2 plus 5/2 is 4/2, which is 2. And positive 1/2 plus 5/2 is 3. And so the answer we get is that in B coordinates, this is the vector 2, 3. In other words, if I take 2 of these vectors and 3 of these vectors, that adds up to negative 1, 5, and that checks. And so if we want to go from standard to alternate, we multiply by P inverse. So converting from coordinate system to standard coordinate, we can multiply by whatever this vector matrix P is. And if we want to convert back into alternate coordinates, we can multiply by P inverse. Part 3 says to do what we have just done here, compute the inverse of the matrix A, and then compute. So here I'm calling the matrix A instead of P. That's okay. Then compute the inverse times negative 1, 5. That's actually what we did here. We have already done part 3 of this problem, instead of doing this by row reduction. This is a fact that we're going to be using later on today, though, that we can convert between standard and alternate coordinates by multiplying by either P or P inverse. So let's go ahead and dig into chapter 4.3 now. All right, so let's look at this matrix here, 1, 2, 2, 1. This matrix has eigenvectors 1, 1, and negative 1, 1, and the eigenvectors are 3 and negative 1. You can check that on your own, but I'm giving you this information for right now. So we know that the linear transformation, if I take this matrix A and multiply by x, that linear transformation is going to scale this vector by a factor of 3 and this vector by a factor of negative 1. That's the definition of an eigenvector, that A times x is equal to just lambda times x. And so A times B1 is equal to 3 times B1, and A times B2 is equal to negative 1 times B2. So we already know this about this linear transformation. This is exactly what eigenvectors and eigenvalues do, is it allows me to replace the A with a scalar. So let's keep going with this example. What matrix has the same effect on the standard basis? In other words, what matrix is it that, and I'll call this matrix D, that D times E1 is just 3 times E1, and D times E2 is negative 1 times E2. What matrix does this to the standard basis? Well, multiplying E1, which is 1, 0, 1 unit in the x direction, 3 times E1 would be 3, 0, and that would be the transformed version of E1. And E2 is 0, 1, And negative 1 times E2 is 0, negative 1. And that's the transformed version of E2. That is, the matrix that operates on the standard vectors the same way that the previous matrix operated on the eigenvectors is just a matrix that has the eigenvalues along the diagonal. So this is why I'm calling this matrix D, is that it stands for diagonal. I'm just putting the eigenvalues going down the diagonal. I'll define that on the next slide, but I think it's a pretty straightforward definition. A square matrix is called the diagonal matrix if it's only non-zero entries are along the main diagonal of the matrix, D11, D22, and so on and so forth. And now we have our definition here. Let's say we have two square matrices. Again, these have to be square. We say that they are similar matrices if there is a basis for each matrix, such the linear transformation A1 scales this basis by the same amounts that this transformation scales this basis. So in the example that we just saw, we saw a matrix that scaled an alternate basis by three units in one direction and negative 1 unit in the other direction. And then we constructed a matrix that did the same thing to the standard basis. Those two matrices are similar. In fact, that's what the next slide says. By the previous example, we know that the matrices A and D are similar. Because this matrix scales this alternate basis by the exact amounts that D scales the standard basis. That is, A times B1 is 3B1, and A times B2 is negative B2. But this diagonal matrix does exactly the same thing, but to a different basis. 3 times E1 and negative 1 times E2. So same scaling factors, different bases. Or another way of saying this is that they have the same eigenvalues but different eigenvectors. All right. But we know how to convert between these two bases. So I'm going to back up to the previous slide for just a second. That is, if I want to convert from this basis to this basis, we know how to do that. To convert from the alternate basis to the standard basis, we multiply by P. When we multiply P, from the standard basis to the alternate basis, we multiply by P inverse, where P is the matrix that we get by putting these two columns together. So 1, 1, negative 1, 1. And so P times X converts from the alternate basis to the standard basis, and P inverse times X converts from the standard basis to the alternate bases. And so if we start in the alternate coordinate system, if we start with a vector that's in b coordinates, then there are two things that we can do that give us the same result. We can either scale that vector using the matrix A. That is, take A times B1, and that's 3 times B1, or take A times B2, and that's -1 times B2. And A times any linear combination of B1, B2. So let's say XY in the B matrix, in the B bases. That's just first column gets scaled by X, so that's going to be 3 times X times B1. And the second column gets scaled by Y, and so that's -1 times Y times B2. Or, and this sounds complicated, but you have actually done this before in another class. And I'll talk about that in a second. Instead of working in the alternate bases, we can convert them to standard coordinates by taking this matrix in B coordinates, converting it to standard coordinates by multiplying by P inverse. Now that we're in standard coordinates, we can multiply this by the matrix D. That D times the standard vectors scale by 3 and 1. So now we're in the standard coordinates, but the matrix D is already in echelon form. It already has a lot of zeros in it. There may be a reason that we would prefer to work with a matrix that's already in echelon form instead of using the matrix A. And then, since we're still in standard coordinates, we then convert everything back to B coordinates using the matrix P. So we're making a conversion that results in a simpler matrix, and then we convert this back. This is like, I won't say it's exactly the same thing, but it's like U substitution. You have a hard integral involving some function of x. You do some conversion into from x's to u's that converts your x's to u's. That function becomes a little bit easier. And then you convert the u's back into x's when you're done. That's the idea, is that you are switching from an x-based coordinate system to a u-based coordinate system. That makes the integral easy. Then you switch back from the u-based coordinate system to the x-based coordinate system. And that gives you the original answer. That's what we're doing here, but we're doing this with the vectors instead of functions. Is that instead of having to work with the matrix A, we can work with a slightly simpler matrix, D. So this is the matrix A, this is the matrix D, and this matrix is a little simpler because it's already in echelon form by doing a conversion back and forth between coordinate systems. And so let me go on to the next slide here. This should be an equal sign, not a minus sign. Sorry. So the matrices A and B, this is a theorem, and it's the theorem that we're going to use next time, are similar if and only if there is a change of coordinates matrix P so that the matrix A and B are related by this conversion P times this matrix times P inverse. In this case, we were converting using a diagonal matrix, and that's going to be usually, so we're going to use this with a diagonal matrix D. But this is a test for matrices being similar, that matrices A and B do the same thing, but in different coordinate systems. The matrix P converts, excuse me, converts back and forth between those coordinate systems, and that gives us the way of testing that A and B are similar. So what we're going to do next time is we're going to look at some problems where the problem is easier to solve by doing this conversion process, by converting from alternate coordinates to standard coordinates, working with a diagonal matrix and standard coordinates, and then converting back. So the next time we're talking about the process called diagonalization, which is the process that we saw in the previous example. We're going to see some examples where this is used. Okay. But the big picture about diagonalization is the vector version of U substitution. We are converting from one coordinate system to another, solving a problem in the alternate coordinate system, and then converting back when we're done. All right. We are done for today. This was a short day. I will see you next time. You take care.